Let f r to r and g r to r be function satisfying. F is satisfying a functional relation and fx equal to x into gx for all xy belongs to r. If limit x tends to 0, gx equal to 1. What is given? Limit x tends to 0, gx. That means from here if you collect gx function, so it will be limit x tends to 0, fx upon x. This is equal to 1. It is given that this limiting value is equal to 1. Now if we concentrate on this limiting value, limit x tends to 0, fx by x equal to 1. You see that the denominator is tending to 0, this is tending to 0, then the numerator must tend to 0 only, because if it is 0 by 0 form, then only we can get a finite limiting value, right? It should be of the form 0 by 0. So this condition will automatically imply that limit x tends to 0, fx must be equal to 0. Then only 0 by 0 form will come. Now if I take the help of this here, let us write the functional equation f of x plus y equal to fx plus, let me replace y by h. Put y equal to h in the functional equation. In this functional equation, so it will be f of x plus h equal to fx plus fh plus fx into fh. So in the right hand side, we can write it as fx plus, from these two terms fh common, 1 plus fx into fh. Now let us take limit on both sides. Limit h tends to 0, limit h tends to 0, f of x plus h is equal to, this is a independent of h, fx plus 1 plus fx into limit h tends to 0, fh. I have taken h tends to 0 on both sides, okay, because as we know x and y, they are independent variables, there is no connection. So x and h, they are independent values. So I have taken in this functional equation, I have taken h tends to 0 on both sides. So limit h tends to 0, f of x plus h is fx plus 1 plus fx into limit h tends to 0, fh. Now we know that limit x tends to 0, fx is 0. So that means this value will be equal to 0. This limit is equal to 0. That means this limit is equal to fx. So we can say that limit h tends to 0, f of x plus h is equal to fx for all x belongs to r. This one we have proved. And what does it mean? This means that fx is continuous. Fx is continuous for all x belongs to r. Because what we have proved is the limiting value is equal to the function value. Okay. Actually, we can prove LHL, RHL also. Both are same here only. If we replace h by minus h, we can prove the LHL equal to function value. It's the same thing. So the function value is equal to the limiting value. That means fx is continuous for all x belongs to r. Now the first option says fx is differentiable for all x belongs to r. So let us test for differentiability. So let us find out limit h tends to 0, f of x plus h minus fx divided by h. What is this limiting value? So from here, from the functional equation, so this was our functional equation, f of x plus h. So this was our functional equation. So from this functional equation, let us substitute this value. So this will be equal to limit h tends to 0, f of x plus h minus fx. f of x plus h minus fx will be this part. So that will be a 1 plus fx into fh divided by h. Now 1 plus fx can be taken out of the limit. So this will be 1 plus fx into limit h tends to 0, fh by h. Limit h tends to 0, fh by h. Now what is the value of this? This value is given in the question. Limit x tends to 0, fx by x is 1. It is already given. So this limiting value is 1. So that means this is equal to 1 plus fx. 1 plus fx. Right? So what we have proved is that the RHT, the right hand derivative is equal to 1 plus fx. RHT is equal to 1 plus fx. And we have already proved that fx is a continuous function. fx is a continuous function. That means fx is taking some real finite value at every point. fx is taking real finite value at every point. So for every possible values of x, this is going to be a real finite value. So I can confirm that RHD equal to some finite value. For different x, the different fx value will come, but it will be some finite value. So RHD is finite. Similarly, replacing h by minus h, we can prove LHD is also same finite. So this will imply that fx is differentiable. Fx is differentiable for all x belongs to R, and this is nothing but the derivative of the function, which is f dash x. So f dash x is equal to 1 plus fx. F dash x is equal to 1 plus fx. So that much that we have proved. Now, so we got the differential equation here. That is, so first option is correct. Fx is differentiable for all x belongs to R, and f dash x is equal to 1 plus fx. This is the differential equation that we have got from here. Now, if we verify that what is the function, if you want to solve, before that, let me calculate what is f dash 0. Put x equal to 0 here. If we put x equal to 0, we will get f dash 0 equal to 1 plus f0. Now what will be f0? Function is continuous at every point. So f0 should be equal to the limiting value as it extends to 0. Limiting value as it extends to 0 is what? 0. So that must be the function value. So f0 must be equal to 0. So this is 1 plus 0. So that is 1. So we can say derivative value at 0 is 1. So option D is also correct. Now let us try to solve this differential equation. So let me write it as f dash x minus fx is equal to 1. We can pre-multiply or multiply e to the power minus x on both sides. Then left hand side will be the derivative of e to the power minus x into fx. Derivative is e to the power minus x. Integrating both sides, we will get e to the power minus x fx is equal to minus e to the power x plus c. So multiplying e to the power x on both sides, fx equal to minus 1 plus c into e to the power x. I have multiplied e to the power x on both sides. Now to find out the c value, what is the condition? The condition is that f0 value is equal to 0. f0 is equal to 0 because the limit value should be equal to the function value. The limit value should be equal to the function value. So f0 must be equal to 0. So using that, what is the c value? So here f0 is equal to minus 1 plus c, that should be equal to 0. So c should be equal to 1. So that means fx, we got the function fx is equal to e to the power x minus 1. We have solved for the function fx as e to the power x minus 1. Now the derivative f dash 1 is equal to, we can now find the derivative f dash x is equal to e to the power x at x equal to 1. F dash 1 will be equal to e. The derivative at 1 should be equal to e. So option C is not correct. And option B says that g0 equal to 1, then g is differentiable at every x belongs to 1. Now let us define the function gx. What is the function gx? Gx is equal to, from here gx is what? Fx by x. Gx equal to fx by x. Of course, when x not equal to 0, and it is given at 0, the function value is 1. So it is 1 when x is equal to 0. We'll be defining the function gx like this. I am taking option B. g0 is 1. So gx is fx by x when x is not equal to 0, 1 when x is equal to 0. That means fx, if we substitute now, fx is e power x minus 1 divided by x when x is not equal to 0, and it is 1 when x is equal to 0. So this is the piecewise definition of the function gx. Now it is saying that g is differentiable at every x belongs to R. Is the function differentiable for all x belongs to R? Where non-differentiability can come for this function? You see, the non-differentiability can come where there is a different value assigned to the function, that is x equal to 0. So we need to just test for differentiability at x equal to 0, because that is the only point where it can be non-differentiable. So let us test for differentiability at x equal to 0. First of all, let us test for continuity at x equal to 0. Continuity of the function at x equal to 0, limit x tends to 0. What is the function? E to the power x minus 1 by x. What is this limit value? We all know that this limit value is equal to 1 and that is equal to the function value g0 equal to 1. So gx is continuous at x equal to 0. Next, let us test for differentiability. For differentiability, we need to test limit h tends to 0 g of h minus g0 by h. Is this limit finite? Let us find out limit h tends to 0. gh is e to the power h minus 1 by h minus g0 is 1 by h. So this value will be limit h tends to 0 e power h minus 1 minus h by h square. Is this limit finite? Yes, we can use the expansion. It is going to be limit h tends to 0 e to the power h is 1 plus h square by 2. We can stop minus 1 minus h by h square. So 1 cancels, h square by 2 by h square. We are getting the value as half. So that means the function g is differentiable at x equal to 0, and if it is differentiable at x equal to 0, it must be differentiable everywhere in real domain. So this option is also correct.